So in the previous video we have seen how to draw complementary CMOS circuits. We have already seen the design of an AND gate too. Now let us take a random Boolean expression and try to implement using complementary CMOS logic. Okay, so this is the Boolean expression I am taking, y equal to a and b plus cd plus e plus f, right? So this is the Boolean expression I am taking. So the circuit will be somewhat bigger because as you can see we have a lot of inputs here. So the number of inputs here is 1 2 3 4 5 6 inputs. So the circuit will contain 2n number of transistors, that is 12 transistors. Why 12? Because to give each input we will have one NMOS transistor, right? And 6 NMOS means if you make it dual you will get 6 PMOS also. So 6 plus 6 will become 12. So when you want to implement n number of inputs or a logic with n number of inputs, you need 2n number of transistors. Okay, that have to be noted. Okay, so in the previous video also we have seen that to implement a 2 input NAND gate we have used 4 transistors, as you can see, 2 PMOS transistors and 2 NMOS transistors to implement a 2 input NAND gate. That's the idea. 2 input means what? N is 2, the input number of inputs is 2, so 2n will become 4. So that's the basic idea. So if at all if I design for this, if you have understood the design completely, you can pause the video and design it by oneself and you can later check it. If you are not so clear, I hope this will give you some clarity, right? So first of all, I'll start implementing from AB. First let me implement the pull down network and I leave the pull up network to you, right? So let me implement the pull down network. Okay, so AB plus CD plus E plus F, right? Let me draw a line like this so that I'll get some space. Okay, so AB plus CD plus E plus F. So AB are in AND operation. Okay, they are implementing AND operation. So let me draw AB first. In when you make 2 NMOS transistors in series means that will become A and B. That's it, right? So this will become A and B. Then CD are in series, that is AND operation, and they together in parallel because there is a plus. So AB is in series, C and D are in series, and together AB and CD they together are parallel. Okay, so AB are in series, C and D are in series. These two series combinations are in parallel. This has to be on parallel means what? You have to couple like this and you have to couple like this. This is the parallel. This is the parallelism, right? And this is in turn parallel with E and parallel with F. In turn parallel with E and parallel with F. So you can put one more transistor which is parallel with these two, and you can put another transistor which is parallel with these three, right? So you have to couple everything. Couple the source and drain, that will become parallel. Connect the source of one transistor to the drain of another transistor, that will become series, right? That's the simple idea. I hope you understood this. This will give you what? A and B are in series, right? So A and B are in series means I'll write A and B. C and D are in series means, so I'm writing C and D. E is a separate transistor, so there is no operation, it's simply E. And F is again a separate transistor, I'll put F. All these are in parallel, as you can see, all these are connected together, node to node, they are end to end connected, so they are parallel. I can put some plus here. Okay, so that's how we implement, and you have to invert it. Anyway, you know that it will give you the output only in inverted form. So y equal to AB plus CD plus E plus F the whole bar, right? Now I will go to implement the pull up network. This is the pull down network which uses some transistors. I will implement the pull up network also. You know that pull up network is dual to pull down network. Here A and B are in series. A and B are in series. So I will make it parallel in the pull up network. So first of all I have to make it A and B as parallel. So A and B. So I'm making them parallel. Again, here all are in parallel, right? So that is all the terms are in parallel combination, as you can see here. So in pull up network all the terms will be in series combination. That's it, all the terms will be in series combination. That have to be kept in mind. So okay, so A and B are parallel here because A and B are in series here, so that will become A and B as parallel. Okay, so C and D are parallel here, I mean C and D are series here, C and D are in series here, so that will become parallel here. C and D are will become parallel. Okay, C and D will become parallel, and as you can see here, they are in series. That means the combination AB and CD are in series. The combination is in series, they are not end to end connected, whereas here the combination is in parallel. The combination is in parallel. That's it. That's how the duality is achieved. Then you have to use two more transistors, right? And they both have to be in series. Okay, this is E and this is F, because they are parallel to all the combinations. They are parallel. Here they will become series. That's it. Okay, so pull-up network are dual to pull-up network is dual to pull-down network. That's how it is achieved. So that's how you convert any Boolean equation into a complementary CMOS circuit. What you have to do is you have to design this, and you can simply take the transistors and arrange in this manner, and you can easily fabricate an IC, right? Again, fabrication in the sense, I mean the design part. Again, we cannot fabricate it standalone. Some support is needed from the industry or whatever. The support is needed. You can only do the design. So that's how we do the design. Okay, so you can, this is one of the ways in order to make the logic into a VLSI circuit. That's how you make it. And again, this has to be grounded. Okay, if you want, you can try it for a 2-input NOR gate, which can be given by y equal to a or b the whole bar. 2-input NOR gate, where you have to make two transistors in parallel in the pull down network, and in the pull up network they will become series. Okay, that's how the implementation goes. I hope you understood this. Thanks a lot.